morning. It's so nice to see everyone. I hope you are all as excited as I am to be kicking off this new Watson lecture season. And if this is your first Watson lecture, welcome. I'm Dr. Crystal Dilworth. I am a neuroscientist, a science communicator, a Caltech alumna, and your enthusiastic host for this program. The Watson Lecture Series is a beloved part of the Caltech tradition, and it's been connecting the university with the public for over 100 years, which is pretty cool. I think 104, I think. It started with a physicist, Earnest C. Watson, who was doing amazing science experiments and demonstrations for the public in what's now the Richard Feynman Lecture Hall over there in East Bridge. And it moved here to the Beckman Auditorium in the 60s. And since then, it's been supported by the Friends of Beckman Auditorium organization, and they also support other performing arts programs here on campus. So I'd like to take a moment to kind of thank them for their legacy of support. Another modern addition to the Watson Lectures was the Junior Watson program. And that's the opportunity for students to come to campus, tour labs, talk to researchers, and learn what it's like to study science and engineering here at the California Institute of Technology. So this month's Junior Watsons are here from Bosco Tech, so let's give them a particularly warm welcome. So as I said before, the Watson Lecture started with a physicist. If you know any physicists, they'll tell you that that's exactly how things should or always did start, was with physics. And so we're going to take their advice, and that's what we're doing with this series. Now, as a member of the Caltech community, it's really easy to kind of take for granted the scale of physics that is being pioneered here on campus. I mean, everything from quantum measurements to astronomical phenomena. We just celebrated the 10th anniversary of the detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory. And you know, if you weren't impressed by the 100 years that scientists had to wait from Einstein's prediction of gravitational waves to its eventual detection, you know, then maybe you would be impressed by the 1.3 billion light years that the waves themselves had to travel in order to be detected by an instrument that, you know, was so sensitive that it could detect perturbations in space-time that are about, like, what, 700 trillionths of a human hair? You know, that's scale. Tonight's speaker, Nick Hutzler, is no stranger to using small clues to tell a big story. And before he tells us what matters about matter, I had to do it, I'm so sorry. You're going to first hear an introduction to him and a little bit about his career by the division chair for the Physics, Math, and Astronomy division here at Caltech. And then you'll watch a video that will tell you a little bit more about him as a person. After that, you will get a chance to ask some of your questions. So the way that that works is a QR code will appear here on the screen. You can use your phones to take a picture. That will send you to Slido. You can type your questions in. It'll come to me here on the iPad, and hopefully I'll get a chance to ask most of your questions during the Q&A. If that doesn't work for you and you prefer a more analog approach, flag down one of our ushers. They should have a comment card that they'll be able to submit and get your question uploaded to the iPad so that I can see it and hopefully ask it. And then after all of that is over, please join us for tea and coffee on the patio and a little bit more time with tonight's speaker. All right, that is it for me. So if you would take the moment to please silence your watches, your phones, your lab mates, anything that you brought with you that makes noise. And please note your nearest exits. Please help me welcome to the stage the leadership chair for Caltech's Division of Physics, Math, and Astronomy, Professor Hiroshi Ooguri.
Good evening. Can you hear me? Good. Good evening, everyone. Welcome to today's Watson lecture. It's a joy to see so many of you here, all gathered to share this evening of science together. Tonight's speaker, Nick Hutzler, is one of my colleagues in the Division of Physics, Mathematics, and Astronomy. Before you hear from him, I'd like to tell you a little about why his kind of research matters. One of the central missions of physics is to discover the fundamental laws of nature and to use them to explain natural phenomena, ranging from property of elementary particles all the way to the beginning of the universe. For much of the past century, the popular public image of the quest toward the most fundamental laws of nature has been particle accelerators, gigantic machines smashing particles together at ever higher and higher energies. That approach, called high-energy physics, has been extraordinarily successful, leading to the discovery of quarks, the W and Z bosons, the Higgs bosons, and more. But going to higher and higher energy is not the only way to peel back the layer of nature. Another equally powerful path is precision. By measuring things with extraordinary care, you can sometimes learn just as much, and sometimes even more, about the universe than by building a bigger accelerator. The idea goes back to the very beginning of science. So let me take you to ancient Greece. Astronomers then could not build space telescopes, but they could still measure. By observing the apparent size of the moon and by watching lunar eclipses, they estimated both its size and the distance. Using similar idea, Aristarchus of Samos concluded, correctly in principle, if not perfectly in numbers, that the sun is much larger than the Earth. I regard it as one of the most important discoveries of ancient astronomy. The sun is bigger than the Earth. Therefore, he argued that it made more sense for the Earth to orbit around the sun than the other way around. That was a valid scientific argument for the heliocentric model of solar system. So you might ask, well, why was it not accepted? Because of precision limits. If the Earth really moved around the sun, the star should appear to shift in the sky from summer to winter, a phenomenon called parallax. The ancient Greeks looked for it carefully but saw nothing. The star looked fixed. It turns out that even the nearest star is more than 4 light years away. To see the parallax, you need to resolve the angle by 2/10,000ths of a degree. That was beyond the ancient Greek technology. They concluded that heliocentric model was wrong since its prediction was falsified. But it was only their lack of precision. In other words, deciding the two-world view required more accurate measurement. The same story repeats through science. Think of Cavendish in the 18th century, carefully measuring tiny gravitational pull between lead spheres to weight the Earth. Or Michelson and Maury in the 19th century, whose exquisitely precise experiment paved the way for Einstein's theory of relativity. Tonight's speaker, Nick Hutzler, continued in this grand tradition. He develops tabletop experiments using lasers to control atoms and molecules with exquisite care. With these tools, he and his collaborator can search for tiny effects that would reveal new physics, effects such as an electric dipole moment of the electron. So why is that important? According to the standard model of particle physics, the electron's dipole moment is predicted to be non-zero but unimaginably small, far too small to be detected. But many proposed theories that goes beyond the standard model predict much larger values. So if you can measure with enough precision, one of the two things happen. Either you discover new effects that open door to new physics, or you set a more stringent limit that rule out entire class of speculative theories. Either way, you shape the direction of fundamental science. Nick stands in a long tradition of scientists stretching back to Aristarchus, each one showing that with clever idea and patient measurement, even the smallest of experiment can transform our understanding of our universe. And tonight, he will show us how precision experiment on the tabletop can speak to the deepest mystery of nature. So before he's being introduced, we'll see a short video about him. So please enjoy.
I grew up in La Crosse, Wisconsin. My mom was a teacher, so learning was always a really big part of the household. I do remember watching a lot of Bill Nye the Science Guy.
Science rules.
And I was really into computers and technology. I visited Caltech when I was a sophomore. The excitement here in the labs, it really clicked with me. I wanted to be a mathematician, but I think I realized over the course of my undergraduate education that what I was really, really interested in was the experimental work. I'm Nick Hutzler. I'm an assistant professor of physics here at Caltech. I'm also an undergrad alum, and I'm an experimental scientist who studies quantum-controlled molecules for fundamental physics. Most of what we do is really weird. We're trying to answer this very fundamental question about where everything in the universe came from. You can convert energy into mass through E equals mc squared. But whenever you create matter out of energy, you also create antimatter in equal amounts. People usually don't know what it is because there isn't any of it. So why would you know what it is? If you want to study it, you basically have to go to a laboratory to create it. We're trying to study that problem just by studying electrons and protons and neutrons, but looking for a signature that this process imprinted on regular matter. The large metal chambers are what we use to make the molecules, and then the lasers are what we use to interrogate and control and probe and study the molecules. Even though I like fiddling with the knobs, the people in the lab they're better at it than I am, and I think my skills are better utilized just kind of helping think and brainstorm and troubleshoot. Not being afraid to tackle some weird problem is maybe a theme in the people who are attracted to our group. I feel like I've gotten lucky with every person who's been in the group, but I think maybe that's just a pattern about the kind of people here at Caltech are really amazing. When you go to get a coffee at Caltech, the people in line in front of you are talking about PCR or something. Being surrounded by those conversations can spur a lot of connections that we would have never made otherwise. I think that environment is really helpful. I spend a lot of time outside the red door, and I definitely spend some time in some secret, quiet reading spots that I discovered as an undergrad that I'm not going to share. A lot of what we're doing is motivated by these very abstract, fundamental, foundational questions. Not just because they inspire awe and wonder, but also because they either will eventually lead to practical things, or they will just lead to a deeper understanding of our universe. Hi, everyone. Thanks a lot for the very nice introductions, and thanks a lot to all of you for coming here tonight. I'm excited to tell you about some of the work we've been doing here at Caltech along the lines of molecules, mysteries, and the matter of existence. We are a group of researchers interested in using quantum science to explore the universe's biggest mysteries. The types of tools that we use, if you got a chance to see outside, involves things like lasers and a lot of glowing things. And that's going to be a recurring theme throughout this talk. First, I'll tell you a little bit about what the big mysteries are that we are studying, how we can investigate these mysteries, and what molecules have to do with any of this. One of the questions we're interested in exploring is a pretty basic one. What is the universe made out of? Well, about 70% of it is dark energy. It's something that gives energy to the universe to make it expand. And we don't know what it is, so I'm not going to say anything else about it. 25% of the universe is dark matter. There's something that pulls with gravity, but we can't see it. And we don't know what it is, and so I'm not going to say anything else about it. This remaining small sliver of 5% is everything we understand in the universe. Atoms, molecules, electrons, planets, stars, everything in between. However, we have no idea where it came from. So there are a lot of pretty big open questions out there. And I'm going to focus on this mystery here. Where did this come from? So I'll quantify a little bit what I mean when I say we have no idea where it came from. So we know a lot about where the universe came from and how it started. It started with a Big Bang, which was a tremendous release of energy. And through Einstein's famous E equals mc squared relation, that energy turned into stuff. It turned into particles, matter. As the universe expanded and cooled, eventually there wasn't enough energy to just start making new particles out of the energy from the Big Bang anymore, and we were sort of stuck with what we had, and the universe, all those particles cooled and condensed into gases and planets and stars and everything else. And this is an extraordinarily, amazingly successful picture, and it explains a lot of what we know about the universe to exquisite detail. But there's a slight caveat, a missing piece, which is whenever you have energy and you use it to create matter, to create particles, you always create an exactly equal amount of antimatter, antiparticles. So after the Big Bang, we should have ended up in a universe with equal amounts of matter and antimatter. The energy can be turned into either one, and it always turns into both equally. So we should have a universe with Spock, but also anti-Spock, or mirror Spock. But there is no antimatter in the universe, not just no anti-galaxies or anti-stars. There's really no antimatter anywhere, and no anti-Spocks, which is, well, I was going to say maybe that's a good thing, but that's a bad thing. Anyway, watch the show. And this is a mystery. We don't understand why there's no antimatter, why there's no anti-Spock in the universe. You may not know what antimatter is because there isn't any of it, so I'll tell you a little bit about it. Every matter particle type has an antimatter partner with all of the same properties except equal and opposite charge. So you all know and love the electron. You're made out of a lot of electrons. There's a type of particle called the positron, which is like a positive electron. It has all the same properties except it's positively charged, unlike the negatively charged electron. And antimatter, it sounds mysterious, and I guess it sort of is, and we don't know why there isn't any, but that's not to say it hasn't been studied. It's actually been studied very extensively in the laboratory, so a tremendous amount is known about antimatter. You can create it in the laboratory by taking some form of energy and converting that into antimatter and matter, and then you can study that antimatter. It's hard to study because the reverse of this also happens. Whenever matter and antimatter touch, they turn back into pure energy. They annihilate back into pure energy. So it's hard to study because you can't really put it in a bottle or anything because it would annihilate the bottle, the container you put it in. As a side note, antimatter was discovered at Caltech. So this is Carl Anderson. He built a device that allowed him to study some of the basic properties of particles, like their charges and their masses. And what he saw was he could see some electrons. He was studying particles coming from cosmic rays. He saw electrons, which people knew and understood, but he saw a signature of something that looked exactly like the electron, but had a positive charge. And so this was the discovery of antimatter. This was the first antimatter type of particle. Since then, many types of antimatter particles have been discovered. And this was a really important advance in fundamental physics that happened right here at Caltech. And there's a plaque commemorating this on East Bridge, that building that you heard about before with the Feynman Lecture Hall, which is one of the main physics buildings. It's a historic physics site of the American Physical Society because of this really amazing discovery that happened there. But it didn't happen there. So where is Carl Anderson in this picture? He is in an engineering building. He's in Guggenheim. But there's no way that the physics department is going to let that plaque go on an engineering building. So it's on the physics building because it's close enough. So I said there's no antimatter in the universe. There's a little bit of antimatter in bananas. Bananas release about 1 particle of antimatter per hour, typical sized banana. And that's true. And the reason that they do that is because they have a lot of potassium in them, which is one of the reasons they're very good for you. And naturally occurring potassium has some slight radioactivity. And however, I got a court order that I had to say that bananas are safe. You could not physically eat enough bananas to make the radiation dose come anywhere close to being remotely dangerous, so it's okay. But apart from the little bit of antimatter in bananas and what you work really hard in the lab to create, we're still left with this really big problem that the universe is essentially entirely matter and there's no antimatter, and we don't understand that. So everything we know about always makes equal amounts of matter and antimatter. So all the physics we know has some balance, some symmetry, in particular between the way it treats matter and antimatter. What we are looking for is something else, something we don't know, maybe some new particle, some new force, some new form of energy, something which only creates matter. So we're looking for something that's imbalanced or a violation of symmetry. So we're looking for symmetry violation. This is a phrase that I'll use quite a few times throughout this talk. We're looking for something that violates the symmetry between matter and antimatter and ultimately led to a matter-filled universe. How can we investigate these mysteries? There are many ways you can do that. One is, like Professor Ooguri said, you can use particle accelerators. So the idea of particle accelerators, like the LHC shown here, which is a very large instrument in Europe, the idea of how they work is you take, in this case, protons, and you smash them together with such high energy that energy creates new particles. So new particles come flying out of these collision sites, and that's actually how they work, which is really amazing. And this approach has been used to discover much of what we know about fundamental physics. But it's not the only approach. You can also just look very closely at regular matter, regular atoms, regular protons and neutrons and electrons, and see if you see some signatures of new interesting particles or forces or forms of energy interacting with them. In our lab, this is what we do. We take this approach, but Caltech does both of these approaches in many different ways, looking for many different types of fundamental mysteries. One of the sources of inspiration for this approach is Chen-Chung Wu, who made a very foundational discovery in physics, in particle physics and nuclear physics, not by using a big high-energy collider, but by just looking at the behavior of nuclei, regular nuclei, very, very carefully. And she discovered, just with a relatively small tabletop-type apparatus, she discovered some very fundamental properties of the universe. And she's kind of the inspiration for this whole approach, this tabletop precision approach. So what do you see if you take something like an electron and you look at it very closely, you'll see a bigger electron. But you will also see something really interesting if you can look close enough. You'll see not just the electron, but the electron surrounded by a cloud of virtual particles flickering in and out of existence. So you'll see like a quantum fireworks show around this electron of all these different particles. Where these particles come from is from the electron's energy. E equals mc squared. The energy of the electron, the intrinsic energy of the electron, can be used to create these new particles. And very interestingly, this cloud of particles around the electron and every other particle contains every possible particle. The energy from the electron can be used to create any particle, including undiscovered ones, including symmetry violating ones, including the ones that we're trying to look for to answer these very fundamental questions about where everything in the universe came from. This idea was really worked out by Richard Feynman, which is a name you heard earlier if you were listening closely. He was a Caltech professor, and people really like him around here. He made a lot of really important discoveries, and one was sort of figuring this out. If you look around campus, you'll see things that look like these Feynman diagrams. I don't think there are any in this room, unfortunately, but this is a very elegant, graphical, diagrammatic way to understand this process of particles. So these lines indicate different particles, and every time there's a split, that's a particle just sort of popping out of the energy of one of the particles and then interacting with other particles. So you'll see these a lot around campus in like architectural elements and graphical elements, because they have a really important connection with physics and Caltech history. They were also on Feynman's van. So that really is Feynman's van. You may notice this is right out front. This was a few years ago for the Feynman 100th birthday celebration. And if you don't believe me that it's Feynman's van, it even had the really expired Caltech parking permit in it still. So what does this have to do with molecules? Well, like other things, like the electron or the nucleus, if you look closely enough at a molecule, you will also see a quantum fireworks show, particles flickering in and out of existence. But importantly, this type of symmetry-violating particles that we are interested in are actually amplified a lot in molecules compared to other things that you could look at. And what they're observable is that they modify molecular properties, but very, very slightly. But we can use quantum measurement tools to study these molecules and try to look for signatures of these small changes in their properties, which is what I'll tell you about. So we're an experimental group. So we actually want to do experiments with molecules. And so there are a few steps before we can actually study something. First, we have to pick what we're going to work with. We have to design or choose our molecule. So I'll tell you a little bit about how we do that. We make a wish list. And a few things on the wish list are, we want a very heavy nucleus. It turns out that large, heavy nuclei are especially sensitive to these fundamental symmetry violating properties. We would like a molecule that we can use laser-based control so that we can use a lot of modern quantum tools, which are based on lasers. We also want some more technical things, like we want the molecule to be very protected from electromagnetic interference. You know, the world is full of electromagnetic noise, and we want to make sure that this flickering that we measure in the molecule is from some interesting particle and not a flickering light bulb on the other side of campus. So we take all of these design elements and we combine them. We try to combine them into a molecule that we can actually work with in the lab. So we start with, honestly, just at the chalkboard. We brainstorm, we ask around, we try to get some insight from chemists and quantum scientists and try to think, okay, what sort of molecules should we be looking at? Eventually, we'll narrow it down. We'll come up with some candidates that seem promising. We'll maybe look at them on the computer and make a short list, and then eventually have to make a determination. And here's one. We work with several molecules in our group, but this is one of them. radium OH, radium monohydroxide, RaOH. And that's one of the molecules that came out of this design process because it's very sensitive to symmetry violation. It plays very nicely with lasers, and it's very insensitive to electromagnetic noise. So it has basically all the properties that we want. One of the reasons why that particular molecule, there are a lot of reasons why that particular molecule is one that we like, but one of the more unusual reasons maybe is that it has a very interesting nuclear shape. Most nuclei are very well described as being either almost perfectly spherical or slightly oblong in one direction. So shaped like an orange or a watermelon. Almost all nuclei are shaped very much like that. Some nuclei, a very small number of nuclei, have this kind of shape. It's a very rare shape, and when a nucleus has this shape, it amplifies symmetry violation by a factor of usually 1,000. So there's a dramatic amplification of these effects that we want to measure. So we're looking for these rare avocado-shaped nuclei. And by the way, the deformation of these nuclei is so large that this actually is sort of an accurate description of how disproportionate it is. Like, these nuclei are very unusual and very rare. And radium is one of the very few nuclei that has this property. So that's one of the reasons why it popped out of our design process. So this looks great. Let's use this molecule. But we're experimentalists, so now we have to start asking some practical questions. And then it gets a little complicated, because it turns out that this molecule is radioactive, chemically unstable, poisonous, and was at least previously unstudied. But otherwise, it's perfect. And so we're going to just check off the design stage, and let's go do it. So we're going to make it in the lab. So first, you have to get radium. So RaOH, oxygen, hydrogen, those are easy to find, but radium's not as easy to find. So where can you buy it? You can buy it on the internet. And this is a real listing. That's the actual, we actually ordered this. That's my order number. And the reason you can buy it on the internet is because radium used to be used to make glow-in-the-dark paints before people knew how very dangerous it was. But there are so many of these around. In fact, there's actually a very good chance that some of you in the audience may have these radium-painted watch hands. You can just buy them online from watch repair supply eBay vendors. And that's what we actually did for our first radium samples. We used those. But maybe not surprisingly, the consistency of those was not very good. They weren't designed to be scientific instruments. So eventually we had to do something a little more sophisticated. So we obtained 1 milligram of radium, which you can't see, but it's like a little sort of grain of sand at the bottom of this vial. If you don't do metric, it's about 0.00003 ounces. So it's a very, very small quantity, but it's intensely radioactive. And so we have to handle it in this special Caltech isotope lab, which is something that it's actually very rare for a university to have something like this. We're very fortunate that we can handle this type of material here. And in addition to being intensely radioactive, it's intensely expensive. So this grain of sand cost about $20,000. And you may have, if you've been keeping up with the news, which maybe you shouldn't be, gold is going for like $4,000 an ounce. But if you do the math, that has nothing on radium, which is going for like $600 million an ounce. So you should invest in radium. So we have the radium now, but we have to make this molecule. And you'd like to do something like, I don't know, mix it with water, and maybe you'll get some chemistry and RaOH will form. And that doesn't really work. And it doesn't work because RaOH is just too reactive. All the molecules we work with in our group are too reactive. They react with everything. It reacts with itself. It reacts with all solid materials, so you can't put it in any sort of container. It reacts with air, it reacts with water. It reacts with everything. So the only place that you can reasonably work with a molecule like this is in an inert gas like helium cooled to minus 450 degrees Fahrenheit. That's the only place where this molecule will survive long enough for you to study it. And that's exactly what we do in the lab. You saw, this is the apparatus that people were working on in that video, by the way. And it even kind of looks like that. So we call this the mini fridge because it sort of looks like a refrigerator and it's very small. And it does fit on a tabletop. And so this is in Downs Lauritsen, if you're ever interested in coming by. Inside here, there's a copper box cooled to minus 450 degrees Fahrenheit, or about 4 Kelvin. We fill it with helium gas, and we put in some radium and then some reactants, some other things we want to react with the radium to make our molecules. And then we have some windows because we're going to be shooting some lasers through here later, fairly soon. The first laser is we vaporize. We have an intense laser pulse that vaporizes some radium and some of these reactants. And since this is happening, so we get some very hot atoms ejected off of these samples. And since this is all happening inside of a very cold helium gas, and helium is chemically inert, it cools these atoms. So now we have cold atoms. We don't want cold atoms, we want cold molecules. And the reason that we are working in this unusual environment is because the chemistry is basically stopped. It's sort of too cold to have any chemical reactions, which is why RAOH would survive once we make it. But it also means that doing the chemistry to make the molecules in the first place doesn't happen. So we shoot a laser in. So we excite the atoms. We give them energy to react with each other by exciting them with an intense laser beam. And then we can create RAOH molecules or other molecules that we want to work with in the lab. And this is all still happening in this cold helium gas environment. So now we have cold molecules that we can study in the lab. So we've now made them, and we can move on to studying them. And we can't do something like this because you can't actually touch the molecules with anything. They're too reactive. You can't physically probe them. The only thing that we can really do to interact with them in a way that won't destroy them is to use light. So how do we use light? We use light to really study the electrons in the molecule. So atoms and molecules are made of positively charged nuclei with negatively charged electrons orbiting around them. Because of the laws of quantum mechanics, those orbits can only exist at very particular discrete values. And the electrons can jump between these different orbits. And you can make them jump, for example, by shooting a laser at them. And after you shoot a laser at them and make them jump into one orbit, after a while they'll jump back into their original orbit, and when they do that, they will emit light, which is called fluorescence. And that light is completely unique and characteristic to every atom and molecule. So we shine a laser through this copper box, and we look to see if the molecules are fluorescing. And if you got a chance to see the demo outside, that's basically what we do in the lab. So this outside, you may have seen something like this. This is a glass tube filled with molecular iodine, which is safe. It's not radium. And when you shine a laser through it, it glows. And if you also looked through that tube attached to that stand, you saw that there was actually some structure in the light coming out. So these molecules were not just emitting light, they were emitting light with some very interesting structure over a very wide range of wavelengths or colors. And this emitted light reveals the molecular structure. So you can look at this, if you can study this carefully enough, you can actually learn a lot, or maybe even everything about this molecule. And that's essentially what we do in the lab, except we have to use better lasers and higher quality spectroscopic tools. So what are we looking for? So those are the tools we use, but what we're looking for are these symmetry violating particles. And we use the fact that, well, this nucleus, the electron, they have this quantum fireworks show going on. They have these particles flickering in and out of existence around them. And those particles flickering in and out of existence modify the properties of these orbits in a very characteristic way that you can study with lasers. This is what one of these spectrometers looks like in the lab. So it's more sophisticated than the cardboard tube because we have to we want very, very high precision for these experiments. But the operating principles are almost exactly the same. We have molecules which we send in a beam down this way. We send lasers through this way, and then these are used to collect the light, the fluorescence from the molecules that we can then analyze to study the molecules. Now, if we want to push these measurements to the most extreme sensitivity, we have to tame the quantum wave functions of the electrons. We have to be able to access the fully quantum nature of the atoms and molecules via their electrons. So we have to sort of confront the fact that these aren't really classical orbits like a planet around a star. They're actually some sort of wave-like orbit due to the wave-particle duality of quantum mechanics. So we have to access this wave-like nature of electrons. The reason that we're so interested in pushing this sensitivity higher and higher is because the better the sensitivity, the better chances we have of detecting these exotic particles or forces or sources of energy that we're looking for. This is sort of analogous to the double slit experiment in quantum mechanics. You take two things and you run them into each other, and if you can access them with enough resolution to see their quantum mechanical nature, you see wave-like interference patterns. And this is what we do in the laboratory with these molecules. We take quantum states, we take these orbits in the molecule, and we watch them interfere with each other. So this is not data from the lab. This is a cool graphic showing the double slit experiment. But we do see these wave-like interferences due to the quantum nature of these orbits of the electrons in the molecule. And this is what we do in the lab to try to look for these small shifts in molecular properties. So we are bringing engineered molecules into the realm of quantum control so that we can explore the mystery of the missing antimatter. And this idea of using quantum science and quantum tools to do fundamental physics searches is one that's really growing on campus. You may have noticed coming in that there's a construction site. This is California Boulevard. And this building is the Dr. Allen and Charlotte Ginsberg Center for Quantum Precision Measurement. And this will be the first center to unite researchers in precision measurement, quantum information, and the detection of gravitational waves. The idea of this building is to bring together quantum scientists and precision measurement people to try to merge these two fields and use the tools of quantum science to make fundamental new discoveries. And this building should be opening next year, so come back and check it out. It should be very cool. I'd like to thank the group that did all of the work that I showed, and all of the agencies and organizations and people who make all of our research possible. So in particular, a lot of our people were supported through Caltech, through fellowships that were very generously given, and our research is supported by a number of agencies and foundations. I'd like to thank you for coming. I invite you to come to the lab anytime, but maybe not literally anytime. You should call first, but we'd love to have you. Thank you.
All right, it's time for you all to get your questions answered. So let's see what you've got for Nick. As I'm getting set up here, Nick, watching you explain sort of how research in your lab goes, I'm struck by two things. One, this is a lot of work. And things are very, very small. Why can't you just have ChatGPT do it all for you?
Yes. Well, I actually have asked ChatGPT some fundamental, basic questions I knew the answer to about this sort of stuff,
Yeah.
and it generally didn't give good answers.
Not impressed?
No.
You wouldn't accept it as a grad student?
No, depends how much it costs. Yeah.
That's an honest answer. I like that. Okay, wow. I've got so many questions here. Let me see. I feel like I know the answer to this question. Is there a mainstream movie or show that provides an accurate or reasonable approximation of the science around antimatter or anything related to your work?
Whoa, that was very specific.
That may have depict science happening at Caltech.
Yeah, I can think of something. Yeah, there's this show, The Big Bang Theory, which I've actually never seen a single episode of it. Not because I'm against it or anything. I just haven't seen it. But I do know some of the people. I know that they take inspiration from actual science experiments and things. And I know some of the people who made some of the doodads that they described on the show as being sort of like ridiculous, impossibly sciencey sounding things. And I'm like, oh, I know the person who made that. So.
I mean, I did, when I saw your presentation first in the rehearsal, I was like, he's the real live Leonard. So I guess there are aspects of that show that are real.
I don't know who Leonard is, but
that's okay.
You
are the inspiration.
I really hope that was a compliment.
He gets a girl.
Okay.
Yeah. Okay, the next one that has a lot of votes is, if you touch hands with your antimatter twin, would you explode?
Yes. Yeah. So you would convert into basically pure gamma radiation. So it's not recommended. But even you'd have to ask, like, if you were in the same room, you'd have to be breathing air, or they would have to be breathing anti-air. The air and the anti-air would annihilate. So I think there's just a lot of logistical problems to that in the first place.
It'd be a difficult experiment to set up.
Yeah.
Okay.
And not one I would sign up my students for.
And in a more serious note, naturally, where does asymmetry exist? And are there any examples of molecules in nature that show asymmetry and benefits to asymmetry?
So the type of asymmetry that I've been talking about, this symmetry violation, matter antimatter, that actually has been observed in the particles that we know, but it's a very, very small amount. It's effectively zero. And so when I talk about it, I usually simplify it and say it doesn't exist. We never observe this. We actually do observe it, but we observe it something like 1 billion times weaker than we would need to explain a matter-filled universe. Yeah, so in some sense, these symmetry violations do exist. They have been observed. Actually, so Chen-Chung Wu, I didn't get a chance to talk about what she did, but she actually discovered a symmetry violation, not a matter-antimatter symmetry violation, but she discovered a symmetry violation of handedness. Like, she basically showed that sometimes when particles are spinning one way versus the other way, they actually behave completely differently. Not just like they're spinning the other way. They almost behave like they're different particles. That's what she discovered, and that's another really important example of asymmetry in physics, very fundamental asymmetry. So there actually are a lot of important examples, but there are also a lot of still unsolved mysteries about asymmetry.
It seems so difficult to build experimental setups that can get to the level of resolution that you and your team are working in every day. And now we have the Ginsberg Center, which is going to be doing similar things with all kinds of different applications. Can you speak a little bit to the type of character that it takes to be that type of experimental physicist?
Yeah, and my group is mostly over there, so thank you. Yeah. So there was a slide that I cut which talked a little bit about how we do the handling of this radium. And one of the steps is dissolving it in a high temperature acid. And so our group attracts the type of people who are like, oh, we have to work with hot radioactive poisonous acid? Sign me up. So that's the kind of people who join our group. So thank you.
Thank you. Not me. How much of your work do you view as being truly physics, and how much of it is chemistry, math? Is there a line between those anymore?
Not really. I think that simply because we're working with molecules, we have to work very closely. In fact, one of the people at the booth is Professor Tim Steinley, is a chemist. So we have to work very closely with chemists. We learn a lot from them. And a lot of what we do in the lab has flavors of chemistry, like I was talking about making, like driving chemical reactions to make the molecules, but this is like a physicist's take on chemistry, because I think when actual chemists make molecules, like they don't do this. But there's a lot of like influence from chemistry. But I'd say if you walk into our lab, it looks much more like a physics lab, because all the chemistry is sort of happening inside these cryogenic chambers. So it's definitely the interface, though. But I'd say we're mostly physicists who are trying to learn and steal as much as we can from chemists.
And I think all research is kind of, it requires that cross-functional collaboration. I don't know that we can really stay in our silos anymore.
Yeah, and we've had a lot of really great interactions with the chemistry department here at Caltech, and we have ongoing collaborations where we're both trying to use each other's tools to solve problems.
But a clear differentiation between us and engineering, just to be clear.
You don't get the plaque.
No.
But yeah.
One of the junior Watsons is asking if these experiments could lead to discovering higher dimensions within particle physics, and perhaps inspired by the three-body problem.
Yeah, so some of I think one of the advantages of the approach that we take is that it's very sensitive to a very, very wide range of physical theories, which is kind of why I was maybe almost vague to the point of being unclear. It was like, are we looking for a particle or a force or like some sort of energy or something? Like the reason that I don't have to specify is because the methods we use can detect any of those. And there are definitely, I think there doesn't have to be connection with what we're looking for and say extra dimensions. But for example, a lot of the proposed solutions to this problem would include extra dimensions that would show up in our experiment and maybe also show up in other places as well. So it could be connected, but because we don't know what it is, we don't know if it's connected or not.
I think that also connects to the question about what is your opinion of string theory?
I don't know much about it, yeah. Okay. I think just as an experiment. So I do know that we look to string theory a lot to get inspiration for a lot of the theories that explain the types of, or that predict the types of things we're looking for. Because you should ask, okay, what we're looking for, is there any chance that it could be there? Especially because we actually don't even know what we're looking for.
Sounds like grad school to me.
Yeah, exactly. I did grad school also doing something kind of similar where we didn't know what we were looking for either.
Did you find it?
So that hit home. But
ignored my question.
Yeah, I'm going right past that one. Yeah, so string theory is something that we definitely invoke a lot along with other theories to say like, well, string theory predicts generically that like these types of particles exist, so there's some motivation to look for them. But I don't know much about it, but we definitely we take a lot of guidance from it and any other theories that try to explain these big open questions in physics.
Speaking of those open questions, and like at least we think we know what we don't know, which is always dangerous. But so one of the questions here is like, how are we sure that the universe is 70% dark energy and 25% dark matter if we can't see it and don't know what it is? How can you confidently make this statement?
Yeah, that's a great question. And I think dark matter in particular, there's been a long history of people trying to come up with alternative explanations, none of which really panned out, except the dark matter explanation, which is just that there's some massive matter that pulls gravitationally but doesn't interact with light at all. And this was originally described, this was originally observed when people like Vera Rubin were looking at galactic rotation curves. So just meaning you look at a galaxy and you see how quickly are things rotating the further you get out from the galactic center. And it's basically like a freshman physics problem to calculate what should that look like in terms of you can measure how many stars are inside, figure out the mass, solve for what the galactic rotation curve should look like. But then when you observe it, it's completely different. And that was sort of the first hint. And people said, well, okay, maybe, but maybe just gravity behaves differently on very long length scales. But then people saw that these types of effects also existed on much shorter scales. And then people did large cosmological surveys and found that all the structure and everything about the universe is consistent with the dark matter hypothesis. And so I would say the reason that I would say, I would never say we know anything really, but the reason that we think it's there is because it's consistent with a very large number of essentially independent observations that all point to the same conclusion, which is that about a quarter of the universe is some non-luminous dark matter. But it could be something, it could be something else, but I don't think anyone has come up with an explanation that is maybe more compelling or satisfying than that one. But it is weird though, because it's like we don't know what it is, but we know it's there. It's like that sounds kind of like a strange thing to say. But there's so much data to support that conclusion.
Junior Watson's future thesis topics, opportunity, something to think about. So Nick, you were an undergraduate here at Caltech, so I have to ask a couple of questions about that. One, what house were you in?
Ricketts House. Yeah, with those two.
Wow, only a few people clapped. Everybody knows the Ricketts reputation for being troublemakers, I suppose. As an undergrad, did you see yourself doing this work? Was there anything that you worked on as an undergrad that directly contributes to the work that you're doing now, or any particular experiences or internships that you think shaped your career? Other than all of them.
It was definitely, so if you paid very close attention to the video, which I know you did, I think I said I wanted to be a mathematician when I got here, but then something made me want to do physics. But that something was doing physics research through the SURF program, which I did.
What is the SURF program?
Oh yeah,
for those
so
of
SURF
us that
is
don't know?
Summer Undergraduate Research Fellowship. So it's
I'm not E.
Yeah, yes, SURF with a U. And I did a physics SURF, I think mainly because I didn't have enough preparation coming in to do a math SURF, but also I think I just realized that it's good preparation to just try other things. I thought physics was cool, so I'll just try doing some physics research. And I ended up really liking it. It was just something I'd never had an opportunity to do before. And I very, very much enjoyed it. And then so that was at JPL. So I did a JPL SURF.
I was going to ask, so you went from math to experimental physics?
Yes,
Okay.
yeah, I went straight to experimental physics. And I really liked it.
What did you like about it?
I liked the hands-on aspect of it, which was just something I just had no experience with before. But I really liked building things. And so then after the first SURF, I did another SURF and research during the school year with Professor Brad Philippone, who does research trying to answer these types of symmetry-violating questions, using a very different approach, using neutrons. But I worked on that experiment, and I thought it was really cool that you could basically search for new fundamental particles and forces by doing sort of low energy precision type measurements instead of very high energy measurements. And so that's what got me interested in this approach.
You started out here, you ended up here. Is there something special about physics at Caltech that drew you back to the community? Or maybe I should ask, what is special about the physics community here? I mean, we saw so much of the history, throughout your talk.
Yeah, the history is cool. I think so Guggenheim, it's across the street from my lab. So if I'm giving a lab tour, sometimes someone will ask some question about antimatter or something, and I'm like, antimatter was discovered on the other side of that parking lot.
It's casual.
And it's where else can you say stuff like that? I guess nowhere. But
It's true.
But I think the thing that I really like most about Caltech now is I think the same thing I liked about it as a student, which is that it's very small and everyone's on the same team supporting the research. So not everyone here is a researcher, but everyone gets it, everyone's on the same team.
Yeah.
Like everyone is pushing towards that goal. And I think I really appreciated that then, and I really appreciate that now.
I have one more question here that's been significantly upvoted. So I guess I should ask it. Sam, you're coming through with all the big questions. So if you could choose the next scientific breakthrough in your field, meaning something that you believe would lead to revolutionary change, what would it be?
It's sort of a broad answer, but there are a lot of experiments like ours trying to look for what people call new physics. New physics is sort of a defined jargony term that just means new fundamental physics outside of the standard model of particle physics. So like a new fundamental particle or a new fundamental force or something. So for example, people trying to find dark matter, or people trying to observe axions, or people trying to find supersymmetric particles. And I think any one of those would be very revolutionary because we don't really have a good idea of what else is out there, which is kind of an unusual situation for physics to be in, because I think previously we always knew what the next discovery was. We had to go do it. Or we didn't always know that necessarily, but for a long time we kind of knew what would be around the next corner. But now we don't, because I think maybe 20 years ago we knew it was around the next corner, and we looked and it wasn't there. Well, I guess, okay, we looked, there was the Higgs boson, which was there, but there was also a bunch of other stuff that was supposed to be there, and none of it was there. And that's kind of a recurring theme in a lot of this fundamental physics now, is that there's sort of a similar story with dark matter. I think people basically knew what dark matter was 10 or 20 years ago, and they didn't actually know what it was, but they're like, it has to be this. And it's like, it turns out it's actually not that. And that kind of keeps happening, and I'd say we're kind of at the point now where we don't really know what the next big discovery will be. But I think any one of those would be really important, because it would help a lot of the other experiments kind of figure out where to point the telescope, proverbially, just because we really have no idea what it is we're supposed to be looking for, which is kind of strange, but also sort of exciting.
Is that the moment when physics becomes philosophy?
Which moment?
The moment when you realize you really have no idea?
No, that's called grad school. Yeah. No, meaning I think that's when you realize you're like, I don't know what's going on. Yeah.
Well, I can't top that. Everyone, please help and thank Nick for his time. Stand up. Have a good evening.